So our next speaker is Tsung Wei Huang from University of Wisconsin at Madison. And Dr. Huang is an assistant professor in the ECE department at the University of Wisconsin at Madison. He was an assistant professor at the University of Utah from 2019 to 2023. Oh, okay, let's get started.
I hope I won't take too much time. So hello everyone, my name is Tsung Wei Huang, and you can just call me TW, which is easy to remember. So today I'm going to talk about parallel and heterogeneous timing analysis, and this is going to be the talk that will summarize what we have been doing in partitioning, algorithm, and system to accelerate static timing analysis. So most of you already know static timing analysis is a very important step in the overall design flow because it verifies the expected timing behavior of your circuit, and basically we want to make sure all the signal can arrive on time. And the term static means we want to analyze the worst case scenario around the clock. So there's always this constraint before clock coming from a set of time constraint that tells you what the lattice arrival time you should have for your circuit design. And also the timing constraint, hold time constraint after the clock that tells you what the earliest possible required arrival time is. Looks like this is not working, but anyway. Okay, so based on this idea, we can always come up with a interval for every endpoint that tries to tell you your signal should always arrive on time within this interval. And the challenge of STA is, modern circuits are very, very big. We may have to analyze a circuit of multi-millions of gates and nets. As the circuit size keeps increasing, the time we spend on static timing analysis also grow exponentially. So that is why exactly we want to parallelize STA, because it will advance the runtime performance to a new level. For example, with 40 CPU, we may reduce the runtime by 10x. Using one GPU, we can further bring another 10x to the performance improvement. When it comes to CPU parallel STA algorithm, existing timer, including commercial tool, typically will levelize the circuit into a bunch of levels and perform level by level propagation using parallel pipeline or something that can parallelize the linear sequence of tasks. And of course, the concept of this pipeline-based parallelization is very simple, but it also has a very, very big issue that we cannot move on to the next level until previous level finish, even though there are some tasks that can actually run in parallel between different levels. So that's the problem of levelization-based approach. So we have tried to come up with a new paradigm, new ways to address this issue. Instead of using pipeline, we come up with a task graph that allows us to model the entire timing propagation in a computational task graph. This task graph can actually more naturally model your timing propagation and flow the computation asynchronously with your circuit network. So in terms of runtime comparison between levelization-based static timing analysis and parallel task graph-based parallel STA algorithm, which we implemented in our open source timing analysis tool, OpenTimer V1. That is levelization-based parallel timing propagation algorithm implemented using OpenMP. And version 2, we implemented the task parallel timing propagation as we just presented from the previous slide. And it's based on our task flow system. And in general, you can see by using task graph parallelism, the runtime can outperform levelization-based method. It can also scale much better regardless of the number of cores that you use to parallelize your STA. And this is because by using task graph parallelism, we can more asynchronously flow the computation along with your circuit network. So although this task parallel STA has certain runtime advantage, it comes with certain overhead. And task parallel STA has two runtime components. So number one goes to building a task dependency graph, or TDG for short. Number two goes to run the build task dependency graph, and this is where all the actual parallelization happens, right? We have this dependency graph, and then we schedule it using a task graph runtime and to parallelize the dependent tasks. And the problem is, if you look at some of these very, very large circuits, they can induce a very, very big task dependency graph, such as a graph that has over 10 million tasks and 10 million dependencies. And the time you spend on building the graph can take more than 50% of the entire runtime. And the other issue is, scheduling a very big task dependency graph has a very, very big scheduling cost. And if you look at some of the existing systems, typically scheduling a task will take about 500 to 1,000 nanoseconds, or it should not be microseconds. And there's certain costs. And there's also some other runtime costs happening around dependency breaking, dynamic load balancing, and worker notification, and so on and so forth. And interestingly, in practice, looking at this task parallel SDA, the performance usually saturates at about 8 to 16 cores. And that means we actually don't need such a big task dependency graph of 10 million tasks or 10 million dependency, right? Because ultimately, we may only need about 16 CPU threads to parallelize execution. So we want to partition a large task dependency graph into a smaller version that allows us to minimize the task dependency graph construction time, and that goes to the static overhead for this task parallel SDA algorithm, and minimize the task dependency graph scheduling overhead. It goes to the dynamic overhead of the task graph parallelism. Okay? So for example, instead of having a big task dependency graph like this with 7 tasks and 1, 2, 3, 4, 5, 6 dependencies, we can partition this into a smaller version that has only 3 tasks and 2 dependencies. Now this is not a very easy task because it is very different from the conventional circuit graph partitioning. In conventional circuit graph partitioning, like what you just saw from the first session, we want to minimize the cut of the partition so we can reduce the communication and interconnect capacity among different partitions. However, partitioning a task dependency graph, we want to reduce the graph size without impacting too much the original parallelism described in the task graph. And there are also some other constraints that we have to worry about when it comes to TDG partitioning. For example, we cannot spend too much time on TDG partitioning, right? Otherwise, the time you spend on a partitioning will outweigh its advantage. And of course, we cannot introduce silly task dependencies such as merging these 2 tasks together and these two tasks together will introduce a cycle in the merged task graph, and this will not be schedulable. And finally, which is the most important part, is we cannot introduce too much sequential parallelism. For example, instead of merging these three tasks together that result in a sequential chain of execution, we can change the partition into another manner that allows us to come out with a smaller task graph, but at the same time we can also maintain certain parallelization. To overcome these challenges, we have recently introduced a GPU accelerated task dependency graph partitioner for STA. And this has a name called GPASTA, which is going to appear in this year's Design Automation Conference. I'm not going to go too much detail, but basically the idea is we are trying to partition the graph in a level by level fashion. At each level, we know all the nodes within the same level can run in parallel, so we can assign each GPU thread to perform the partition. So when we move on to the next level, each GPU thread will try to decide what parallel task it wants to merge its assigned task to. So we can run the whole thing level by level in a parallel fashion using GPU. Okay. So in terms of experimental result, on the table over here, we have the TDG runtime after the STA runtime after we perform the partitioning. And as you can see, in general, by reducing the STA task graph to a smaller version, we are able to introduce another 50% to 2x performance improvement. Comparing our method, GPasta, with the state-of-the-art GDCA partitioning algorithm, which is a very famous task dependency graph partitioning algorithm in the parallel computing community. By using GPU, our partitioning runtime can be up to 40x faster. So when it comes to using this partitioning algorithm in a real STA software tool, we can clearly see that our GPasta algorithm can further improve the STA runtime performance by up to 20%, I believe. So now we have understood we can utilize task graph parallelism to make STA run faster, multi-core CPU. So I'm going to talk about why there is a need for CPU-GPU heterogeneous parallelism. In our experiment, we have found that CPU-based parallelization does not scale beyond 16 threads, and there could be multiple reasons around this context of problem. For example, CPU has a very limited flag count and memory bandwidth, and many of these CPU-based algorithms primarily focuses on strong scalability, trying to explore what parallelism I can get from the circuit structure itself. And there's always this Amdahl's law that limits the maximum speed up you can get from the strong scalability. But if you look at the modern static timing analysis workload, we typically have a very big volume of data parallelisms to deal with. We have millions of data to analyze. They can run in parallel across these millions of gates. And we also need to analyze the workload across hundreds of corners and so on and so forth. So there are lots of data parallelism that we can utilize by taking advantage of GPU. So based on this idea, we have introduced quite a bunch of GPU accelerated static time analysis algorithms. For example, in ICCAT 2020, we have come out with a GPU algorithm for graph-based analysis. And later on, we come out with a data structure that allows us to speed up the path generation using GPU and so on and so forth. Just trying to give you a general idea about how GPU can actually help us accelerate static time analysis. So one of the most important parts in STA is generating critical path. Okay? And suppose we have come up with a very efficient data structure that allows us to use a constant time and space representation to represent each critical path. So in this case, we are able to take advantage of massive data parallelisms to generate millions of critical paths at the same time. So based on this idea, we have GPU kernels for speeding up the process of finding shortest path. And based on the result, we also have another GPU kernel that allows us to quickly generate millions of critical paths in parallel. And this slide shows you some example results from our DAC 2021 paper, where we leverage GPU to accelerate the critical path generation, and we also evaluate the quality in the path-based analysis workload to propagate the slew from millions of critical paths. And as you can see from this table, by using GPU, we are able to achieve a very, very big speed up, like over 600x compared to one CPU, of course. Even though using 40 CPU, we are still able to gain 44x speed up when it comes to generating millions of critical paths. So we have been doing quite a lot of task parallel static timing analysis algorithm, and we start to think about we have many of these interesting innovations. Can we generalize all of our innovation to benefit the broader scientific computing application? So we have tried to isolate the core part of our algorithm into a standalone system project. It's called task flow. Remember, the core part in our STA is to model everything in the task graph, so we can quickly parallelize all those irregular workload. So let's take a look at this high-level example in our system. So suppose you want to do 4 things, A, B, C, D, and A has to run before B and C, right? And B will need to run after B and C. So when A finishes, B and C can run in parallel. When both B and C finish, D can start. And this is how it looks in our task flow system. You only need about 15 lines of C++ code. So you can get a parallel execution for this task graph. So first, you will need to create a task flow object that describes a dependency graph from your workload. Then you will define an executor that manages a set of worker threads to schedule your dependency graph. And then you can use the in-place method to create 4 tasks in terms of C++ lambda function objects. And then you can use the presys, the SID method to relay the dependency. Okay? And by this moment, I believe many of you can fully understand what this code is trying to do, even though you may not have that much experience in C++ programming. So that's the power of programming model to simplify the parallel computing. So a major innovation behind our system and existing framework is our control task flow graph programming model that allows you to go beyond the limitation of traditional DAG-based model that you cannot express control flow in a single task graph entity such as cycle, conditional tasking, loop, and so on and so forth. And we also have a very interesting dynamic task graph programming interface that does not allow you to, that allows you to overlap the task construction time and task execution time together. So you can use this interface to dynamically describe a task graph. Every time you create a task, it will immediately start its execution. In this case, you can build a dependency on the fly. When I create a task, I can specify which task it has to depend on. And this allows you to very, very efficiently overlap task construction time and task execution time. So everything is composable in our system. Task dependencies, control flow, they are all associated with each other. And the scheduler will perform a whole graph optimization to enable a very efficient overlap among task and control flow. And this will largely improve your programming productivity. For example, in one of the Reddit posts, the company shared their experience of how task flow helped their company migrate their existing graph analysis engine from TDP to our system in just a few hours, and the result got improved by 8% of performance. Okay? So with that, I'm going to stop here, and we'll be happy to take any questions. Yes?
Thanks, Professor Huang, for your distinguished talk. I guess my questions are kind of trivial. Thanks. I see that in slide page 8, you illustrate that the task flow cannot be scalable for more than 60 cores. And then in later page, you illustrate that this is due to the memory bandwidth, etc. And in your later experiments, you do experiments with one GPU card. So I was wondering, why do you not consider multiple cores, multiple GPU cards, or is there any kind of specific challenge that restrict task flow for the scaling for multiple machines? Thanks.
I guess the question is there any restriction on task flow whether we can schedule it in a distributed environment?
Yes.
So this is a very interesting question. So far, we do not try to extend our system to a distributed environment because there are just too many things that we have to worry about. For example, fault tolerance, when some machine shut down, and how are you going to deal with that? It also depends on the workload. Previously, we do have a distributed version of the system, but we realize with the advances of this GPU and new memory architectures, it may be just push everything into a single heterogeneous node that we can push many things to GPU. And it will give you a much better advantage compared to distributed computing. And for many of these EDA workloads, I would say we do not have that much data compared to Microsoft or Magnificent 7. And our data size is like a medium scale. So if you are able to just push everything into a single heterogeneous node, design a better data structure, design a better data representation, will be much faster compared to distributed computing. Yes.
Yeah, first thank you, because I'm a heavy user of TaskFlow, and thank you for maintaining developing such a good tool. So I actually have two questions, because I did something very similar to that partition-based SDA in my work I just presented. So I have like two more specific questions. First one is, when you partition that, right, the forward propagation and backward propagation have different workloads, because forward is like more determined by the fan-ins, and backward is more determined by fan-outs. And did you do like different partitioning for like different propagation types? Yeah, maybe let me finish the second question also. So the second question is also about that partitioning, right? That is a non-trivial problem, because you need to make sure that the partitioning clusters are acyclic, right? So the way I did it is I just do a topological sort and do chunking. So I feel like different clustering algorithms basically corresponding to a different topological sort with chunking, right? So you didn't show like how much gain you get from different clustering algorithms. You're only comparing cluster versus non-cluster, right? So I just wonder, do you have any sense, like if you do that clustering differently, how much impact it will be?
So thank you for this question. In fact, because of the time limit, I did not present too much detail. And our partitioning algorithm does allow you to specify certain costs during the partitioning. And you can tune the partitioning algorithm to, for example, I want certain costs. I don't want each partition to go beyond certain costs. And in this case, we can assign different costs to, for example, in forward propagation, you might have a much loaded path, and then we can assign a higher cost. In backward propagation, we can assign a smaller cost. And this is something that can be done in our partitioning algorithm. And to your second questions, and I do believe you are right, we can have multiple clustering algorithms, but over here we do not experiment different clustering algorithms, but simply focusing on a partitioning algorithm that can do a much better job for SDA workload. Of course, it can be the future direction.
Okay, thank you. Because we're a little bit over time, so if you have any other questions, feel free to ask Tsung Wei. Yeah,
Thank you.
Okay, thanks for coming. Okay, so our this session ends here, and I think it's lunchtime.
Does he get a prize for us?
Yeah.